tonight we're venturing into one of the most extraordinary discoveries in the history of space exploration. A story so unexpected, so mind-bending, that it forced scientists to completely rewrite everything they thought they knew about where our solar system ends and the vast unknown begins. This is the story of what Voyager found at the edge of our cosmic neighborhood, and trust me, they weren't ready for what was waiting out there. If you find comfort in these gentle explorations of the cosmos, I'd be grateful if you'd consider subscribing and giving this video a like. It helps the algorithm find more curious minds like yours, and it would mean the world to me as we continue these journeys together into the deepest mysteries of space. The visuals are here to guide you, but feel free to close your eyes, breathe deeply, and let your imagination drift alongside these remarkable spacecraft as they venture into the unknown. I'd love to know where you're listening from tonight. Drop your location in the comments below. Picture this moment. It's August 25th, 2012. Somewhere in the vast darkness beyond Neptune, beyond Pluto, beyond anything we've ever explored, a small spacecraft no bigger than a car is quietly measuring something that will change everything. After 35 years of traveling through space, after flying past Jupiter and Saturn and sending back images that redefined our understanding of the outer planets, Voyager 1 is approaching a boundary that exists only in theory. A place where the influence of our sun finally gives way to something else entirely. Something we've never encountered before. For decades, scientists had dreamed of this moment. They had built mathematical models, created computer simulations, and made predictions about what this boundary would look like. They called it the heliopause, the edge of the heliosphere, the cosmic shoreline where our solar system meets interstellar space. It was supposed to be relatively straightforward, a clean transition from the realm of our sun to the realm of the galaxy itself. They were wrong completely, utterly, beautifully wrong. What Voyager discovered out there in the cosmic wilderness wasn't just different from what scientists expected. It was so strange, so contrary to every prediction, that it forced them to question fundamental assumptions about how our solar system works. The boundary wasn't clean. It wasn't simple. It was a chaotic, dynamic, multi-layered frontier filled with phenomena that shouldn't exist according to everything we thought we knew. Let me take you on this journey, step by step, as we follow Voyager into the unknown and discover just how unprepared we were for the reality of interstellar space. Our story begins not with Voyager's final destination, but with the first hints that something was very, very different about the edge of our solar system. In December 2004, Voyager 1 encountered something called the termination shock. Think of this as the cosmic equivalent of a sonic boom, the place where the solar wind, that constant stream of charged particles flowing out from our sun at supersonic speeds, suddenly slams into something and decelerates dramatically. Scientists had predicted this boundary for decades. They knew it had to exist somewhere out there, about 90 astronomical units from the sun, where the solar wind would finally meet resistance from the interstellar medium. What they didn't expect was how violent and chaotic this boundary would be. When Voyager 1 crossed the termination shock at a distance of 94 astronomical units, its instruments detected something extraordinary. The solar wind, which had been racing outward at hundreds of kilometers per second for the entire 30-year journey, suddenly slowed to a crawl. temperatures spiked to tens of thousands of degrees. The magnetic field became twisted and turbulent. It was as if the spacecraft had sailed into a cosmic storm of unimaginable proportions. But here's where the story takes its first unexpected turn. When Voyager 2 approached this same boundary 2 years later, it encountered the termination shock at a completely different location. Not at 94 astronomical units like its twin, but at only 84 astronomical units from the Sun. 10 astronomical units closer. That's a difference of nearly 1 billion miles. This discovery shattered one of the most basic assumptions about our solar system. For generations, scientists had imagined the heliosphere as roughly spherical, like a giant bubble surrounding our Sun and planets. The idea that both Voyager spacecraft would encounter the termination shock at roughly the same distance seemed obvious. After all, the Sun radiates its energy equally in all directions, so the boundary of its influence should be roughly the same everywhere, right? Wrong. The heliosphere, as Voyager revealed, is not a sphere at all. It's asymmetrical, lopsided, shaped more like a comet than a bubble. Something in interstellar space is pushing against our solar system unevenly, compressing the heliosphere on one side and stretching it out on the other. Our entire solar system, it turns out, is moving through the galaxy like a ship pushing through cosmic waters, and those waters are pushing back. This was just the beginning. As both Voyager spacecraft continued their journey beyond the termination shock, they entered a region called the heliosheath, the outermost layer of our solar system's protective bubble. Scientists had predicted this would be a relatively quiet zone, where the solar wind would gradually fade away as it prepared to give way to interstellar space. Instead, Voyager found chaos. The heliosheath turned out to be a cosmic battleground where solar particles and interstellar particles clash in ways that create some of the most extreme conditions in our solar system. Temperatures reached 30,000 to 50,000 Kelvin, hot enough to vaporize any known material. Scientists dubbed this region the Wall of Fire, though the name is somewhat misleading. This isn't fire in any sense we would recognize. It's a plasma so hot and energetic that it exists at temperatures that would make the surface of the Sun seem cool by comparison. Yet despite these incredible temperatures, Voyager sailed through this wall of fire completely unharmed. How is this possible? The answer reveals something profound about the nature of space itself. The wall of fire is incredibly hot, but it's also incredibly thin. The particle density is so low that despite the extreme temperatures, there simply aren't enough particles present to transfer significant heat to the spacecraft. It's like walking through a furnace that contains only a handful of atoms. But the wall of fire was just one of many surprises waiting in the heliosheath. As Voyager 1 continued its journey, it encountered something completely unprecedented. In 2010, at a distance of about 113 astronomical units from the Sun, the spacecraft's instruments detected something that shouldn't exist according to any model of the outer solar system. The solar wind stopped. Not gradually, not slowly, but suddenly and completely. After traveling for billions of miles at hundreds of kilometers per second, the solar wind just stopped moving outward. Voyager had entered what scientists called the stagnation region, a cosmic dead zone where solar particles pile up like cars in a traffic jam, unable to push any further against the mounting pressure from interstellar space. In this stagnation region, something even stranger happened. The magnetic field doubled in intensity, compressed and concentrated by the pressure from outside our solar system. At the same time, high-energy particles from deep space, cosmic rays that had been partially blocked by the solar wind, suddenly increased by a factor of 100. It was as if Voyager had found a leak in our solar system's cosmic shield, a place where the galaxy's most dangerous radiation was beginning to seep through. But the most surprising discovery in the stagnation region was yet to come. Scientists had expected that when Voyager finally reached the boundary between solar and interstellar space, it would encounter a sharp transition: the Sun's magnetic field on one side, the galaxy's magnetic field on the other, probably pointing in completely different directions and creating turbulence and chaos at their meeting point. Instead, Voyager discovered something that shouldn't be possible: a region where the Sun's magnetic field and the interstellar magnetic field somehow connected and merged. Scientists called it the magnetic highway, and it defied every prediction about how magnetic fields behave in space. Think about this for a moment. The Sun's magnetic field originates from nuclear processes in our star's core and extends outward through the entire solar system. The interstellar magnetic field is created by completely different processes involving the rotation of our galaxy and the collective influence of billions of other stars. These two magnetic systems should have nothing in common, no reason to align or connect. Yet somehow, out there at the edge of our solar system, Voyager found a place where these vastly different magnetic fields link up and create pathways for particles to flow between our solar system and interstellar space. Solar particles use these magnetic highways to escape into the galaxy, while cosmic rays from deep space stream inward along the same pathways. The discovery of the magnetic highway was so unexpected that it took scientists years to even begin to understand what they were seeing. It suggested that the boundary between our solar system and the rest of the galaxy is far more dynamic and interconnected than anyone had imagined. Rather than two separate domains with a clear dividing line, Voyager had found a transition zone where solar and galactic influences merge in ways that challenge our understanding of how magnetic fields behave on cosmic scales. As Voyager 1 continued its journey through this mysterious boundary region, its instruments detected another phenomenon that left scientists scratching their heads. The spacecraft's plasma wave instrument, designed to detect electromagnetic oscillations in space, began picking up sounds. Not sounds in the way we normally think of them, since sound waves cannot travel through the vacuum of space, but electromagnetic waves that could be converted into audio frequencies and played through speakers. These cosmic sounds told a story that was both beautiful and puzzling. When Voyager was still inside our solar system, the electromagnetic waves it detected had a low, deep tone, around 300 Hz, like the lowest notes on a pipe organ. This was the acoustic signature of the solar wind, the sparse plasma of our Sun's outer atmosphere, vibrating at frequencies determined by its low density. But as Voyager approached the boundary with interstellar space, these cosmic sounds began to change. The pitch rose higher, becoming more intense and urgent. By the time Voyager crossed into interstellar space, the electromagnetic waves had jumped to frequencies between 2,000 and 3,000 Hz, nearly 10 times higher than what the spacecraft had been hearing inside the heliosphere. These changing frequencies provided direct evidence that Voyager was encountering denser material as it moved into interstellar space. The interstellar medium, the thin soup of gas and dust that fills the space between stars, was revealing its presence through sound. For the first time in human history, we were listening to the acoustic signature of interstellar space itself. But even this discovery came with surprises that challenged expectations about what lies between the stars. The sounds Voyager was detecting revealed that interstellar space is far from the quiet, empty void scientists had imagined. Instead of the serene cosmic silence they expected, Voyager discovered a universe filled with a constant, monotonous hum, a background noise that permeates all of interstellar space like a cosmic radio station that never goes off the air. Dr. Stella Ocker, the Cornell astronomer who led the analysis of these interstellar sounds, described them as faint and monotone, existing in a narrow frequency bandwidth. But within this apparent simplicity lay profound complexity. The spacecraft was detecting the persistent hum of interstellar gas, a plasma that fills the seemingly empty space between stars. This wasn't just background noise, it was the acoustic fingerprint of the galaxy itself. As Voyager continued deeper into interstellar space, these sounds revealed something even more remarkable. The density of the interstellar medium wasn't constant. It fluctuated dramatically, sometimes increasing by 40-fold over relatively short distances. The spacecraft was sailing through invisible waves of matter, cosmic tsunamis of gas and dust that sweep across the galaxy on scales of tens of light years. These density fluctuations told a story of violence and turbulence that exists on scales almost impossible to comprehend. The space between stars, far from being a calm and peaceful realm, is stirred by the rotation of our entire galaxy. As our Milky Way spins through space, it creates massive currents and eddies in the interstellar medium, waves that dwarf anything we experience on Earth. Imagine ocean waves that span entire solar systems, currents that flow for thousands of light years, storms that rage for millions of years. This is the reality of interstellar space that Voyager discovered. The spacecraft had become humanity's first deep-sea explorer of the galactic ocean, sending back reports of currents and waves that exist on scales that challenge human imagination. But perhaps the most puzzling discovery awaited Voyager in the realm of cosmic rays, those high-energy particles that stream through space at nearly the speed of light. For decades, scientists had developed elegant theories about how these particles are created and accelerated. They predicted that the termination shock, that cosmic sonic boom where the solar wind slams into the interstellar medium, would act like a giant particle accelerator. The theory was beautiful in its simplicity. Particles would bounce back and forth across the shock front, gaining energy with each collision like cosmic pinballs, until they were accelerated to incredible speeds and became the cosmic rays that rained down on Earth from all directions. Scientists expected that when Voyager reached the termination shock, it would detect the highest concentrations of these newly minted cosmic rays. Instead, Voyager found nothing. No peak in cosmic ray intensity at the shock. No evidence of the particle acceleration process that was supposed to be one of the primary sources of cosmic rays in our galaxy. The termination shock, rather than being a cosmic particle accelerator, seemed to be relatively quiet when it came to producing high-energy particles. Even more puzzling, as Voyager moved beyond the termination shock and deeper into the heliosheath, cosmic ray intensities continued to increase steadily. Whatever was creating these energetic particles, it wasn't happening at the boundary scientists had predicted. The source of cosmic rays was somewhere else entirely. in a region of space that remained completely unexplored and poorly understood. This discovery forced scientists to completely reconsider their understanding of cosmic ray acceleration. If the termination shock wasn't the primary source they had assumed, then where were these particles coming from? What unknown processes in the outer reaches of our solar system were capable of accelerating particles to such incredible energies? The cosmic ray mystery deepened when Voyager began detecting strange patterns in how these particles behaved. Some cosmic rays seemed to be trapped or deflected by magnetic fields in ways that created pockets of enhanced or depleted particle flux. The interstellar medium wasn't uniformly bathed in cosmic radiation as scientists had expected. Instead, it contained regions of high and low particle density, cosmic shadows, and bright spots that suggested complex magnetic field structures operating on scales never before observed. As Voyager 1 prepared for its final crossing into pure interstellar space, scientists thought they knew what to expect. The spacecraft would cross the heliopause, the ultimate boundary of our solar system, and suddenly find itself in a completely different environment. Solar particles would disappear, replaced by the thin gas of interstellar space. The Sun's magnetic field would give way to the galactic magnetic field, probably pointing in a different direction and creating turbulence at the boundary. On August 25, 2012, Voyager 1 finally crossed that ultimate boundary and became the first human-made object to enter interstellar space. But even this moment of triumph came with surprises that nobody had anticipated. The crossing itself was remarkably subtle. There was no dramatic announcement from the spacecraft, no sudden change that immediately signaled humanity's entry into the space between stars. Instead, scientists had to carefully analyze months of data before they could definitively say that Voyager had crossed the heliopause. The subtlety of the crossing revealed something profound about the nature of this cosmic boundary. Rather than a sharp edge like a cliff face, the heliopause turned out to be more like a shoreline where ocean meets land. There's a definite boundary, but it's complex and dynamic, with waves and tides that blur the exact location where one realm ends and another begins. What made the crossing even more remarkable was what Voyager didn't find on the other side. Scientists had predicted that the interstellar magnetic field would point in a different direction from the Sun's magnetic field. The two magnetic systems, created by completely different processes, should have been oriented randomly with respect to each other. Instead, Voyager discovered that the interstellar magnetic field was remarkably aligned with the Sun's magnetic field. The two fields were nearly parallel, as if they had somehow been coordinated across the vast distances of space. This alignment was so unexpected that it took scientists years to develop theories that could explain what they were seeing. The parallel magnetic field suggested that our solar system's journey through the galaxy is far more complex than anyone had imagined. Rather than plowing through interstellar space like a ship through water, our solar system seems to be following magnetic field lines that connect it to larger galactic structures. The Sun's magnetic field and the interstellar magnetic field aren't separate systems at all, but part of a larger magnetic architecture that spans incredible distances. This discovery had profound implications for understanding how our solar system fits into the larger galactic environment. The magnetic connection between our Sun and interstellar space suggests that what happens in our cosmic neighborhood is influenced by processes occurring dozens or even hundreds of light years away. Our solar system isn't an isolated island floating in empty space, but part of a vast magnetic web that connects stars and stellar systems across the galaxy. As Voyager continued its journey deeper into interstellar space, it began detecting phenomena that revealed just how dynamic and complex this supposedly empty realm truly is. The spacecraft encountered regions where particle densities suddenly spiked or dropped, creating cosmic weather patterns that exist on scales of light years. These variations weren't random fluctuations, but seemed to follow patterns that suggested underlying structure in the interstellar medium. The patterns Voyager detected painted a picture of interstellar space as a place of constant motion and change. Shock waves from distant supernova explosions sweep through the galaxy, compressing and heating the interstellar gas. Stellar winds from massive stars create bubbles of hot, low-density plasma that can persist for millions of years. The collective gravitational influence of billions of stars creates currents and streams in the interstellar medium that flow like rivers through space. All of these processes combine to create an interstellar environment that is far more structured and dynamic than the uniform, static medium that scientists had envisioned. Voyager was revealing that the space between stars is as complex and varied as the space within stellar systems, filled with its own weather patterns, currents, and storms that operate on galactic scales. Perhaps most remarkably, Voyager's journey into interstellar space was providing humanity with its first real-time monitoring system for galactic processes. The spacecraft's instruments were continuously sampling the interstellar medium, tracking changes in density, magnetic field strength, and particle composition over distances of light years. For the first time in human history, we had a probe actively exploring the galaxy beyond our solar system and reporting back on conditions in interstellar space. The data streaming back from Voyager was rewriting textbooks and forcing scientists to develop entirely new models of how our galaxy works. Every assumption about the space between stars was being challenged by direct observations from humanity's first interstellar explorer. And this was just the beginning of the revelations that would emerge from Voyager's unprecedented journey into the cosmic unknown, discoveries that would challenge everything we thought we knew about our place in the galaxy. But the most extraordinary discovery was yet to come. As Voyager 1 settled into its new home in interstellar space, its instruments began detecting something that defied every prediction about what lies beyond our solar system. The spacecraft encountered what scientists can only describe as interstellar weather, vast storms and currents that sweep through the space between stars on scales that dwarf anything we experience in our earthly atmosphere. Picture this cosmic meteorology for a moment. While we think of space as empty and static, Voyager was revealing a universe in constant motion. The interstellar medium isn't a calm ocean, but a turbulent sea stirred by forces operating on galactic scales. Shock waves from exploding stars race through space at thousands of kilometers per second, compressing and heating the thin gas between stellar systems. Massive stars blow powerful winds that create cavities of hot plasma spanning hundreds of light years. And all of this happens in a medium so tenuous that a teaspoon of Earth's atmosphere contains more particles than a volume the size of our entire solar system in interstellar space. The weather patterns Voyager detected told a story of violence and beauty on scales almost impossible to comprehend. The spacecraft was sailing through the aftermath of stellar explosions that occurred when our sun was still forming from the collapse of its own interstellar cloud. It was encountering pressure waves from stars so massive they burned through their nuclear fuel in just a few million years, before exploding with the force of billions of atomic bombs detonating every second for months on end. These cosmic storms don't just affect the interstellar medium, they shape the very structure of our galaxy, carving out bubbles and caverns in space, creating the complex architecture of hot and cold regions that determine where new stars can form and where existing stellar systems like ours encounter turbulence in their journey through space. But perhaps the most mind-bending aspect of these discoveries was what they revealed about time itself in the interstellar realm. The phenomena Voyager was detecting operate on timescales that stretch human comprehension. A single shockwave from a supernova explosion might take hundreds of thousands of years to sweep past our solar system. The currents and streams in the interstellar medium flow for millions of years, carrying material across distances so vast that light itself takes decades to traverse them. Voyager was providing humanity with a glimpse of processes that unfold over geological timescales. Cosmic phenomena that began before complex life emerged on Earth and will continue long after our sun burns out. The spacecraft had become a time machine, allowing us to observe the slow-motion dance of matter and energy that shapes the galaxy over periods measured in millions and billions of years. As the months and years passed, Voyager's continuous monitoring of interstellar space began revealing patterns that suggested an even more profound truth about the nature of our galactic neighborhood. The variations in particle density, magnetic field strength, and cosmic ray intensity weren't random fluctuations, but showed clear correlations with our solar system's motion through space. Our entire solar system, it became clear, is surfing through the galaxy on currents of interstellar matter that have been flowing for millions of years. We're riding waves of gas and dust that were set in motion by stellar processes that occurred before our planet even existed. The very trajectory of our sun through space is being influenced by these ancient currents, carrying us toward regions of the galaxy we won't reach for millions of years. This discovery fundamentally changed how scientists think about our solar system's place in the cosmic order. We're not isolated wanderers drifting through empty space, but active participants in galactic-scale processes that connect us to the larger story of stellar birth, life, and death that plays out across the Milky Way. The implications were staggering. If our solar system's path through the galaxy is influenced by these interstellar currents, then our future cosmic environment is already being determined by processes we're only beginning to understand. Millions of years from now, our solar system might encounter regions of space with very different properties, denser interstellar clouds, or areas swept clean by ancient stellar explosions. These future encounters could have profound effects on our solar system. Dense interstellar clouds could compress our heliosphere, allowing more cosmic radiation to penetrate the inner solar system. Changes in the local magnetic field could affect how solar particles interact with planetary atmospheres. The very climate of worlds like Earth could be influenced by our passage through different regions of interstellar space. But Voyager's revelations about interstellar weather patterns were just one piece of a much larger puzzle that was emerging from the spacecraft's unprecedented journey. The probe's instruments were also detecting something that challenged fundamental assumptions about how matter and energy behave in the extreme conditions of deep space. In the sparse environment between stars, where particle densities are millions of times lower than the best vacuum achievable in terrestrial laboratories, Voyager discovered that conventional rules of physics begin to break down in subtle but important ways. The spacecraft was detecting plasma behaviors that don't occur anywhere else in our solar system, phenomena that exist only in the unique conditions of interstellar space. These exotic plasma physics effects were creating their own mysteries. Voyager's instruments sometimes detected sudden bursts of electromagnetic activity with no apparent source, as if the vacuum of space itself was spontaneously generating energy. Other times, the spacecraft would encounter regions of unusual calm, where the background electromagnetic noise dropped to levels so low that they approached the theoretical minimum possible in any plasma environment. Scientists realized they were witnessing the universe operating in a regime they had never before observed directly. The interstellar medium exists in a state that's neither fully ionized plasma nor neutral gas, but something in between that exhibits properties of both. In this strange twilight state of matter, particles can travel for years without colliding with anything else, yet still maintain electromagnetic connections across vast distances. The study of these exotic plasma states was opening entirely new fields of physics. Researchers had to develop new theoretical frameworks to understand how matter behaves when it's so dispersed that individual particles might be separated by distances larger than planets. The insights gained from Voyager's observations were finding applications in everything from fusion research to understanding the behavior of matter in the early universe. Meanwhile, the spacecraft's journey was revealing another layer of complexity in the structure of interstellar space. Voyager began detecting what scientists called interstellar turbulence, a hierarchy of eddies and vortices in the interstellar medium that cascade from galactic scales down to the size of individual stellar systems. This cosmic turbulence operates according to principles similar to those that govern atmospheric weather on Earth, but on scales that stretch across light years. Just as Earth's atmosphere contains weather patterns ranging from global circulation patterns down to local wind gusts, the interstellar medium contains structural features spanning from the rotation of the entire galaxy down to disturbances created by individual stars. Voyager was sailing through this turbulent medium like a ship navigating an ocean with currents, eddies, and storms operating on scales from meters to thousands of kilometers. The spacecraft's instruments could detect the signatures of these different scales of motion, providing the first direct measurements of how energy cascades through the interstellar medium from the largest scales down to the smallest. This discovery had profound implications for understanding how galaxies evolve over cosmic time. The turbulent motions in the interstellar medium play a crucial role in mixing heavy elements created by dying stars throughout the galaxy, distributing the raw materials for planet formation to regions where new stellar systems are being born. The same turbulence that Voyager was measuring helps determine where and when stars can form, influencing the rate at which galaxies convert their gas into new stellar populations. But perhaps the most philosophically profound aspect of Voyager's discoveries was what they revealed about the interconnectedness of cosmic processes. The spacecraft was showing that our solar system isn't an isolated island of matter and energy floating in empty space, but an integral part of a vast web of relationships that connect every star in the galaxy. The magnetic field lines that Voyager traced extending from our Sun into interstellar space don't end at some arbitrary boundary. They connect to magnetic structures that span the entire galaxy, linking our modest stellar system to the collective magnetic field generated by billions of other stars. The cosmic rays that rain down on Earth originate in stellar explosions thousands of light years away, following magnetic highways that thread through interstellar space for decades or centuries before reaching our cosmic neighborhood. Even the basic elements that make up our planet and our bodies are products of this galactic interconnectedness. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were created in the nuclear furnaces of massive stars and dispersed through interstellar space by supernova explosions. We are quite literally made of star stuff, and Voyager was tracing the pathways through which that stellar material traveled from its point of creation to eventually become part of planets and living beings. This cosmic perspective was transforming how scientists think about life itself. The conditions that allow complex chemistry and biology to emerge aren't just local phenomena determined by planetary processes. They're the result of galactic-scale events that unfold over billions of years. The heavy elements necessary for rocky planets and organic molecules are created in stellar cores and distributed by interstellar processes. The rate of cosmic ray bombardment that drives mutation and evolution is controlled by the local interstellar environment. Even the climate stability that allows life to persist may depend on our solar system's passage through different regions of interstellar space. Voyager was revealing that to understand life on Earth, we need to understand the galaxy itself. The story of biology is inseparable from the story of stellar evolution, supernova explosions, and the complex dance of matter and energy that plays out in the space between stars. As the spacecraft continued its lonely journey deeper into interstellar space, now moving at 17 kilometers per second away from everything it had ever known, it was also moving forward in time, providing humanity with a preview of cosmic futures that await our solar system. The regions Voyager was exploring represent the kind of environment our Sun and planets will eventually encounter as we continue our 220 million year orbit around the galactic center. The data streaming back from this first interstellar probe was allowing scientists to map the cosmic terrain that lies ahead of us, identifying regions of dense interstellar clouds that our solar system will encounter millions of years from now, tracking the motion of shock waves from stellar explosions that might affect our cosmic neighborhood in the distant future. In a very real sense, Voyager had become humanity's advanced scout, reconnoitering the galactic frontier and reporting back on the cosmic weather conditions that await us in the deep future. The spacecraft was providing crucial intelligence about the long-term prospects for our solar system and any life it might harbor as we continue our eternal journey through the galaxy. But even as Voyager pushed deeper into the unknown, sending back revelations that challenged every assumption about interstellar space, the most extraordinary discoveries were still to come. The spacecraft was approaching regions of space that no theoretical model had ever attempted to describe, entering a realm where the very concepts of boundaries and transitions might lose their meaning entirely. The edge of our solar system, it was becoming clear, wasn't an edge at all. It was a gateway to something far stranger and more wonderful than anyone had ever imagined, and more wonderful than anyone had ever. What Voyager was discovering challenged the very notion of what it means to reach the edge of anything. The spacecraft wasn't finding clean boundaries or definitive transitions, but rather a series of nested frontiers, each more mysterious than the last. It was as if our solar system existed within layers of cosmic onion skin, and Voyager was peeling them away one by one, revealing new realms of physics and new questions about the nature of space itself. As the months turned into years and Voyager 1 settled deeper into its interstellar journey, the spacecraft began transmitting data that painted an increasingly complex picture of what lies beyond our cosmic home. The interstellar medium wasn't the uniform, predictable environment that decades of theoretical work had suggested. Instead, Voyager was sailing through a cosmos filled with structure, variation, and phenomena that existed nowhere else in the known universe. The plasma wave instrument continued to detect those haunting electromagnetic sounds, but now scientists were beginning to decode the deeper meaning within those cosmic frequencies. Each subtle change in pitch and intensity revealed information about the invisible architecture of interstellar space. The spacecraft was essentially conducting a vast acoustic survey of the galaxy, using sound waves to map regions of space that no telescope could ever observe directly. What emerged from this acoustic mapping was a picture of interstellar space as a place of incredible complexity. Rather than the smooth, empty void that scientists had envisioned, Voyager revealed an environment filled with invisible structures. Walls of compressed gas stretched across light years, carved out by ancient stellar explosions. Rivers of hot plasma flowed between cooler regions, creating a hidden geography that existed only in the realm of electromagnetic fields and particle interactions. The spacecraft's magnetometer was painting an equally complex picture of the magnetic landscape beyond our solar system. The interstellar magnetic field wasn't uniform or static, but showed variations and fluctuations that suggested a dynamic environment shaped by forces operating on galactic scales. Voyager was detecting magnetic field reversals, regions where the field direction suddenly flipped, creating boundaries and interfaces that affected how charged particles moved through space. These magnetic structures were revealing themselves to be the highways and barriers that control the flow of cosmic rays throughout the galaxy. High-energy particles from distant stellar explosions follow magnetic field lines like cars following roads, creating invisible traffic patterns that span thousands of light years. When these magnetic highways intersect or merge, they create cosmic intersections where particle densities spike dramatically. When they diverge or oppose each other, they create magnetic shadows where cosmic ray intensities drop to unusually low levels. Voyager was providing the first direct measurements of this vast magnetic infrastructure, revealing how the galaxy organizes the flow of energy and matter on scales that dwarf anything in our solar system. The spacecraft had become humanity's first explorer of this hidden realm, mapping territories that exist only in the interaction between magnetic fields and charged particles. But perhaps the most profound revelation was emerging from the spacecraft's cosmic ray detector. The patterns of high-energy particles that Voyager was measuring weren't random or uniform, but showed clear signatures of structure and organization. The interstellar medium was revealing itself to be stratified, layered like an atmospheric system, but operating on scales of light years rather than kilometers. These cosmic ray measurements were providing insights into processes that had occurred millions of years ago and light years away. Each high-energy particle that struck Voyager's detector carried information about its journey through the galaxy, information encoded in its energy spectrum and arrival direction. Scientists were learning to read these cosmic messages, decoding the history of stellar explosions, magnetic field interactions, and interstellar turbulence that had shaped each particle's path to the spacecraft. The story that emerged from this analysis was one of a galaxy in constant motion and transformation. Massive stars lived fast and died young, exploding with such violence that they carved out caverns in the interstellar medium that persisted for millions of years. These stellar explosions didn't just create the heavy elements necessary for planets and life. They also drove shock waves through space that compressed and heated the surrounding gas, triggering new waves of star formation in distant regions. Voyager was sailing through the aftermath of countless such explosions, detecting the signatures of stellar deaths that had occurred when our solar system was still forming. The spacecraft was like an archaeological probe, uncovering evidence of cosmic events that had shaped the galaxy long before Earth existed. Each measurement added another piece to the puzzle of galactic evolution, revealing how the Milky Way had transformed over billions of years from a young, chaotic collection of gas and stars into the mature, structured spiral galaxy we see today. The implications of these discoveries extended far beyond astronomy. The interstellar environment that Voyager was exploring directly affects the conditions within our solar system. The density and composition of the local interstellar medium influences how our heliosphere interacts with galactic space, potentially affecting the amount of cosmic radiation that reaches the inner planets. Changes in the interstellar magnetic field could alter how solar particles escape our system, or how galactic cosmic rays penetrate our cosmic neighborhood. Scientists were beginning to realize that Earth's climate and the evolution of life might be influenced by our solar system's journey through different regions of interstellar space. Periods when our solar system passes through dense interstellar clouds could compress our heliosphere, allowing more cosmic radiation to reach Earth's atmosphere. This increased radiation could affect cloud formation, atmospheric chemistry, and even the rate of genetic mutations that drive biological evolution. The cosmic ray data from Voyager was providing crucial information for understanding these connections between galactic and terrestrial processes. The spacecraft was measuring the baseline cosmic ray environment that our solar system encounters as it travels through its current region of the galaxy. Future changes in this environment could be detected by comparing new measurements with Voyager's interstellar baseline, providing early warning of cosmic weather changes that might affect our planet. Meanwhile, Voyager's particle detectors were revealing another layer of complexity in the interstellar environment. The spacecraft was detecting populations of particles with unusual energy distributions and compositions, particles that seem to have been processed by unknown mechanisms in the depths of interstellar space. These weren't the simple atoms and ions that theoretical models had predicted, but complex mixtures of particles that had been accelerated, decelerated, ionized, and recombined by processes that operated only in the extreme conditions between stars. Some of these particles appeared to be ancient, perhaps originating from stellar explosions that occurred billions of years ago and had been wandering through the galaxy ever since. Others seemed to be freshly created by ongoing processes in the interstellar medium, perhaps generated by the collision of shock waves from different stellar sources, or by magnetic reconnection events in interstellar plasma. The diversity of particle populations was revealing interstellar space to be a much more active and dynamic environment than anyone had imagined. Rather than a passive repository for material ejected by stars, the interstellar medium was showing itself to be a place where new physical and chemical processes occurred, processes that existed nowhere else in the universe and operated on timescales measured in millions of years. Voyager's instruments were also detecting trace amounts of complex molecules in interstellar space, organic compounds that had somehow survived the harsh radiation environment between stars. These molecules were the building blocks of chemistry and potentially of life itself, scattered through the galaxy and available to be incorporated into new planetary systems as they formed. The discovery of organic molecules in interstellar space added another dimension to the story of cosmic evolution. The chemical complexity that allows life to emerge wasn't just a local phenomenon that occurred on planets, but part of a galaxy-wide process that created and distributed the raw materials for biology across vast distances. Voyager was detecting the molecular seeds that might someday become part of living organisms in stellar systems that wouldn't form for millions of years. This revelation transformed how scientists think about the search for life in the universe. The chemical precursors for biology weren't rare accidents that occurred only under special planetary conditions, but common features of the interstellar environment. Every new star system that formed from interstellar material inherited a ready-made library of complex molecules, providing a head start for the chemical evolution that might lead to life. But even as Voyager continued to revolutionize our understanding of interstellar space, the spacecraft was also revealing the limitations of what any single probe could discover in such a vast realm. The regions that Voyager was exploring represented an infinitesimally small sample of the galaxy's total volume. The spacecraft was like a single weather station trying to characterize the entire atmosphere of a planet, providing crucial but necessarily limited information about an environment of almost unimaginable scale. The data from Voyager was raising as many questions as it answered. Each new discovery revealed the existence of processes and phenomena that demanded further investigation. Scientists were identifying regions of interstellar space that showed unusual properties, areas that might harbor unique physical conditions or rare types of cosmic phenomena. But these tantalizing hints could only be fully explored by future missions. Spacecraft that might not launch for decades and wouldn't reach their targets for decades more. The pace of interstellar exploration was fundamentally limited by the vast scales involved. Even traveling at Voyager's impressive speed of 17 kilometers per second, it would take the spacecraft tens of thousands of years to cross the distance to the nearest star. The regions of space that Voyager could explore in its remaining operational lifetime represented a tiny fraction of even our local galactic neighborhood. Yet within this limitation lay a profound lesson about the nature of cosmic exploration. Voyager wasn't just discovering new facts about interstellar space. It was pioneering entirely new ways of studying the galaxy. The spacecraft's instruments were proving that direct, in situ measurements of the interstellar medium were not only possible but essential for understanding how our galaxy works. The techniques that Voyager was demonstrating, from acoustic mapping with plasma waves to magnetic field tracing with magnetometers, were establishing the foundation for future interstellar missions. Each measurement was refining our understanding of what instruments would be needed to explore different regions of interstellar space, what phenomena were most important to study, and what questions should guide the next generation of interstellar explorers. The spacecraft was also proving that interstellar missions could operate successfully for decades in the harsh environment beyond our solar system. Voyager's continued operation more than 40 years after launch demonstrated that human technology could survive and function in regions of space that no engineer had ever been able to test or simulate. This proof of concept was crucial for planning future missions that might need to operate for even longer periods in even more remote regions of the galaxy. As Voyager pushed deeper into the unknown, now more than 20 billion kilometers from home and still transmitting data across the vast gulf of interstellar space, the spacecraft was also becoming a symbol of human curiosity and determination. The probe represented our species' first permanent presence beyond the solar system, a technological ambassador carrying information about Earth and humanity into the cosmic deep. The golden records attached to both Voyager spacecraft contained sounds, images, and messages from Earth, designed to communicate something about human civilization to any intelligence that might encounter the probes millions of years in the future. But in a deeper sense, the spacecraft themselves were the most profound message we could send to the cosmos, a demonstration that intelligent life could arise on a small planet and develop the capability to explore the galaxy. Voyager was proving that the same curiosity and ingenuity that had allowed humans to explore Earth's oceans and atmosphere could also be applied to exploring the galaxy itself. The spacecraft represented the extension of human consciousness into realms that had previously existed only in imagination, making the invisible structures and processes of interstellar space accessible to scientific investigation for the first time. The data streaming back from this first interstellar mission was laying the groundwork for a new era of galactic exploration. Future generations of scientists and engineers would build on Voyager's discoveries, developing more sophisticated instruments and more capable spacecraft to explore regions of interstellar space that remain completely unknown. The techniques pioneered by Voyager would evolve into new methods for studying stellar formation, galactic evolution, and the distribution of life throughout the cosmos. But perhaps most importantly, Voyager was changing how humanity sees itself in relation to the galaxy. The spacecraft's journey was revealing that our solar system isn't an isolated outpost floating in empty space, but an integral part of a vast interconnected web of cosmic processes. We aren't separate from the galaxy. We are the galaxy, made from stellar material and shaped by galactic forces, temporary arrangements of matter and energy that have achieved the remarkable feat of consciousness and curiosity. The story that Voyager was telling wasn't just about the physics and chemistry of interstellar space, but about the deep connections that link every atom in our bodies to the cosmic processes that have shaped the galaxy over billions of years. We are citizens of the Milky Way, participants in a story that began with the first stars and will continue long after our sun burns out, connected to the cosmos in ways we are only beginning to understand. And as Voyager continued its eternal journey into the depths of interstellar space, carrying with it the hopes and dreams of an entire species, the spacecraft was also carrying something else into the cosmic unknown. It was carrying the questions that drive all exploration, the wondering that pushes us always toward new horizons, the insatiable curiosity that transforms us from earthbound creatures into citizens of the galaxy itself. As Voyager's instruments continued their patient vigil in the cosmic deep, something even more extraordinary began to emerge from the data flowing back across billions of miles of empty space. The spacecraft was detecting patterns that suggested the existence of vast structures in interstellar space, architectural features of the galaxy that operated on scales so immense they challenged human comprehension. Picture massive walls of gas and dust stretching across dozens of light years, invisible monuments carved by stellar winds and supernova explosions that occurred when our galaxy was young. These weren't random formations, but organized structures that channeled the flow of matter and energy through interstellar space. Like cosmic highways and barriers, Voyager was sailing through this hidden infrastructure, mapping territories that existed only in the realm of magnetic fields and particle interactions. The spacecraft's plasma wave detector was revealing that these structures had their own acoustic signatures, electromagnetic frequencies that told the story of their formation and evolution. Each wall of compressed gas sang with its own distinctive note, a cosmic choir of frequencies that painted an invisible landscape in sound. Scientists were learning to read this acoustic map, like explorers deciphering the geography of an alien world. But perhaps the most mind-bending discovery was what these measurements revealed about time itself in the interstellar realm. The structures Voyager was detecting had been shaped by events that occurred millions of years ago. The spacecraft was sailing through the fossil remains of ancient stellar explosions, preserved in the architecture of interstellar space. Like geological formations preserve Earth's history in stone. A shockwave from a supernova explosion that occurred when dinosaurs roamed the Earth was still expanding through space, its leading edge now hundreds of light years from its point of origin. Voyager was detecting the subtle signatures of this ancient catastrophe, reading the story of a star's death written in the density fluctuations of interstellar gas. The spacecraft had become a cosmic archaeologist, uncovering evidence of galactic events that predated human civilization by geological ages. These temporal discoveries were reshaping how scientists think about cause and effect on galactic scales. The interstellar environment that our solar system currently inhabits was shaped by stellar processes that began their work when our sun was still a young star and Earth was a molten ball of rock. The cosmic ray environment that affects our planet today carries the signatures of stellar explosions that occurred before complex life emerged in Earth's oceans. Voyager was revealing that to understand our present cosmic environment, we need to understand the deep history of our galactic neighborhood. The spacecraft was providing the first direct measurements of how galactic history is preserved in the structure of interstellar space, showing how events separated by millions of years in time and thousands of light years in space remain connected through the slow evolution of the interstellar medium. The implications were staggering. If the current interstellar environment carries the imprint of such ancient events, then the cosmic conditions our solar system will encounter in the future are already being determined by stellar processes happening today in distant regions of the galaxy. Massive stars currently burning in star-forming regions thousands of light years away will someday explode and send shock waves through space that won't reach our neighborhood for millions of years. Voyager's measurements were providing crucial data for predicting these future cosmic weather patterns. By understanding how shock waves and stellar winds propagate through interstellar space, scientists could begin to forecast the long-term cosmic environment that our solar system will encounter as it continues its quarter-billion-year orbit around the galactic center. But the spacecraft was also detecting phenomena that suggested the interstellar medium itself was far more active than anyone had imagined. Rather than a passive collection of gas and dust left over from stellar processes, interstellar space was revealing itself to be a dynamic environment where new physical and chemical processes occurred continuously. Voyager's instruments were detecting regions where interstellar gas was being heated to millions of degrees by unknown mechanisms, creating pockets of incredibly hot plasma in the cold depths of space. Other measurements revealed areas where magnetic fields were spontaneously reorganizing themselves, releasing bursts of energy that accelerated particles to incredible speeds. The spacecraft was discovering that interstellar space had its own internal sources of energy and activity, processes that operated independently of stellar influence. These discoveries were forcing scientists to completely reconsider their models of how galaxies evolve over cosmic time. The interstellar medium wasn't just a repository for material ejected by stars, but an active participant in galactic evolution. The heating, cooling, compression, and rarefaction of interstellar gas helped determine where and when new stars could form. The magnetic field structures detected by Voyager played crucial roles in channeling the flow of cosmic rays and controlling the rate at which heavy elements were mixed throughout the galaxy. The spacecraft was revealing that galaxies aren't just collections of stars orbiting a central black hole, but complex ecosystems where stars, interstellar gas, magnetic fields, and high-energy particles all interact in ways that shape the evolution of the entire system. Understanding how galaxies work required understanding the intricate dance of processes that Voyager was measuring in the depths of interstellar space. As the months turned into years and Voyager pushed deeper into this cosmic frontier, the spacecraft began detecting variations that suggested it was encountering the boundaries between different types of interstellar environment. The probe seemed to be passing from one cosmic weather zone into another, crossing invisible boundaries that separated regions with different temperatures, densities, and magnetic field properties. These transitions weren't sharp like planetary boundaries, but gradual shifts that occurred over distances of light years. Voyager was sailing through cosmic climate zones, each with its own characteristic properties and phenomena. Some regions were dominated by hot, tenuous gas heated by nearby stellar activity. Others contained cooler, denser material that might someday collapse to form new stars. Still others showed the signatures of ancient supernova explosions, regions where stellar violence had carved out cavities in space that would persist for millions of years. The diversity of these environments was revealing interstellar space to be far more complex and structured than the uniform medium described in textbooks. The galaxy contained multiple populations of interstellar material, each with its own history and destiny. Voyager was providing the first direct survey of this cosmic ecology, cataloging the different types of interstellar environment and measuring how they interacted with each other. But perhaps most remarkably, the spacecraft was also detecting evidence of processes that seem to violate our understanding of how matter and energy behave in extreme environments. In regions where the particle density was so low that individual atoms might travel for years without colliding with anything else, Voyager was measuring phenomena that required collective behavior among particles separated by vast distances. The spacecraft was detecting coherent plasma oscillations that extended across regions larger than our entire solar system. electromagnetic waves that somehow maintained their organization despite propagating through a medium millions of times more tenuous than the best vacuum achievable on Earth. These collective phenomena suggested that the sparse matter of interstellar space could behave in ways that had never been observed in any terrestrial laboratory. Scientists were struggling to develop theoretical frameworks that could explain these observations. The physics of extremely low-density plasmas was largely unexplored territory, a regime where quantum effects, electromagnetic forces, and gravitational influences all played roles that were poorly understood. Voyager was pioneering the exploration of this new frontier in physics, revealing phenomena that existed only in the unique conditions between stars. The study of these exotic plasma states was opening entirely new fields of research. The insights gained from Voyager's observations were finding applications in fusion energy research, where scientists were trying to understand how to maintain stable plasmas at high temperatures. The spacecraft's measurements were also relevant to cosmology, helping researchers understand how matter behaved in the early universe when particle densities were much lower than they are today. Meanwhile, Voyager's cosmic ray detector was painting an increasingly detailed picture of the high-energy particle environment in interstellar space. The spacecraft was detecting not just the overall intensity of cosmic rays, but the detailed energy spectra and composition of these particles. Each measurement provided clues about the cosmic processes that had accelerated these particles to nearly the speed of light. The patterns Voyager was measuring revealed a complex ecology of cosmic ray sources and acceleration mechanisms operating throughout the galaxy. Some particles bore the signatures of recent supernova explosions, their energy spectra showing the characteristic features of shockwave acceleration. Others seemed much older, their original energy signatures modified by millions of years of propagation through interstellar space. Still more mysterious were populations of particles with unusual isotopic compositions, cosmic rays that seemed to have been processed by unknown nuclear reactions in the depths of space. These particles suggested that interstellar space contained its own nuclear laboratories, regions where high-energy collisions between cosmic rays and interstellar atoms created exotic isotopes that couldn't be produced by any known stellar process. The discovery of these unusual cosmic ray populations was providing new insights into the nuclear processes that operate in the galaxy. Voyager was detecting the products of nuclear reactions that occurred not in stellar cores, but in the vast reaches of interstellar space. Reactions powered by the incredible energies of cosmic ray particles, accelerated by galactic-scale magnetic fields. These findings were revolutionizing our understanding of how the chemical elements are distributed throughout the galaxy. The nuclear processes detected by Voyager were contributing to the galactic inventory of rare isotopes, adding another layer of complexity to the story of how stars, planets, and life obtain the raw materials they need to exist. But even as Voyager continued to revolutionize our understanding of interstellar space, the spacecraft was also approaching the limits of what any single probe could discover in such a vast realm. The regions that Voyager had explored represented an infinitesimally small sample of the galaxy's total volume. The spacecraft was like a single weather station trying to characterize the entire atmosphere of a planet, providing crucial but necessarily limited information about an environment of almost unimaginable scale. The data from Voyager was revealing the existence of phenomena and processes that demanded further investigation. But the spacecraft couldn't linger to study any single region in detail. It was racing through interstellar space at 17 kilometers per second, spending only months or years in regions that would take light itself years to cross. Many of the most intriguing discoveries were glimpsed only briefly before Voyager moved on to explore new territories. Scientists were identifying regions of interstellar space that showed particularly unusual properties, areas that might harbor unique physical conditions or rare types of cosmic phenomena. But these tantalizing hints could only be fully explored by future missions. Spacecraft that might not launch for decades and wouldn't reach their targets for decades more. The pace of interstellar exploration was fundamentally limited by the vast scales involved. Even at Voyager's impressive speed, it would take the spacecraft tens of thousands of years to cross the distance to the nearest star. The regions of space that Voyager could explore in its remaining operational lifetime represented a tiny fraction of even our local galactic neighborhood. Yet within this limitation lay a profound lesson about the nature of cosmic exploration. Voyager wasn't just discovering new facts about interstellar space, it was pioneering entirely new approaches to studying the galaxy. The spacecraft's instruments were proving that direct, in situ measurements of the interstellar medium were not only possible, but essential for understanding how our galaxy works. The techniques that Voyager was demonstrating were establishing the foundation for future interstellar missions. Each measurement was refining our understanding of what instruments would be needed to explore different regions of interstellar space, what phenomena were most important to study, and what questions should guide the next generation of interstellar explorers. The spacecraft was also proving that interstellar missions could operate successfully for decades in the harsh environment beyond our solar system. Voyager's continued operation more than 40 years after launch demonstrated that human technology could survive and function in regions of space that no engineer had ever been able to test or simulate. This proof of concept was crucial for planning future missions that might need to operate for even longer periods in even more remote regions of the galaxy. As Voyager pushed deeper into the cosmic unknown, now traveling through space that no human-made object had ever explored, the spacecraft was also revealing something profound about the nature of exploration itself. The probe was discovering that each answer led to new questions. Each revelation opened new mysteries. Each boundary crossed revealed new frontiers waiting beyond. The edge of our solar system hadn't been a final destination, but a gateway to an even grander adventure. The heliopause wasn't the end of the story, but the beginning of a new chapter in humanity's relationship with the cosmos. Voyager was showing us that the universe is far stranger, more complex, and more wonderful than we had ever dared to imagine. The spacecraft was carrying more than scientific instruments into the depths of interstellar space. It was carrying the hopes and dreams of an entire species, the curiosity that drives us to explore beyond every horizon, the wonder that transforms us from planetary creatures into citizens of the galaxy itself. In its lonely journey through the cosmic deep, Voyager was proving that the same spirit of exploration that had once carried humans across Earth's oceans could also carry us across the vastness of space. And as the spacecraft continued its eternal voyage into the unknown, still transmitting data across the growing gulf of interstellar space, it was also transmitting something else. It was transmitting proof that intelligence could arise in the universe and develop the capability to explore the galaxy. That consciousness could emerge from cosmic dust and stellar fire and reach out to touch the infinite depths of space. Voyager was our first ambassador to the galaxy, a technological messenger carrying news of Earth and humanity into regions of space that might not be visited again for millions of years. But in its deepest sense, the spacecraft was something even more profound. It was the universe becoming aware of itself, cosmic matter organized in such a way that it could explore and understand its own vast architecture. The discoveries flowing back from this first interstellar mission were rewriting our understanding of the cosmos, revealing connections and processes that linked every atom in our bodies to the grand story of galactic evolution. We are not separate from the stars and the spaces between them. We are part of the same cosmic web, temporary arrangements of stellar material that have achieved the remarkable feat of consciousness and curiosity. And in that realization lay perhaps the most profound discovery of all. Voyager wasn't just exploring interstellar space. It was exploring the deepest connections between mind and cosmos, between intelligence and the infinite, between the human capacity for wonder and the endless mysteries that await our discovery in the vast cathedral of the galaxy. The spacecraft continued its journey into the depths of space, carrying with it all the questions that drive exploration, all the wonder that pushes us toward new horizons, all the hope that somewhere in the cosmic deep we might find answers to the deepest mysteries of existence itself. But the most extraordinary revelation was yet to come. As Voyager pushed deeper into the interstellar realm, its instruments began detecting something that challenged our most fundamental assumptions about the nature of space itself. The spacecraft was encountering regions where the very concept of emptiness seemed to break down, where the vacuum of space revealed itself to be alive with activity in ways that defied every prediction. Picture this for a moment. In the depths of interstellar space, where the distance between individual atoms can span entire football fields, Voyager was detecting organized structures that somehow maintain their coherence across distances that light takes months to traverse. These weren't physical objects in any sense we could recognize, but patterns in electromagnetic fields, invisible architectures built from nothing more substantial than the interaction between magnetic forces and scattered particles. The spacecraft's magnetometer was tracing these ghostly structures like an explorer mapping the rooms of an invisible cathedral. Magnetic field lines twisted and braided themselves into complex geometries that persisted for light years, creating pathways and barriers that guided the flow of cosmic rays through the galaxy. It was as if space itself had developed a nervous system, a network of invisible connections that carried information and energy across the vast reaches of the Milky Way. What made these discoveries so profoundly unsettling was their implication for our understanding of cause and effect on cosmic scales. The magnetic structures Voyager was detecting weren't random formations, but showed clear signs of organization and purpose. They channeled particle flows, concentrated energy, and created regions of enhanced or depleted cosmic ray intensity with a precision that seemed almost deliberate. Scientists found themselves confronting patterns in the data that suggested intelligence, not in the sense of conscious design, but in the way that complex systems can spontaneously organize themselves into structures that appear purposeful. The interstellar medium was revealing itself to be a vast information processing network, a cosmic computer that used magnetic fields and particle interactions to perform calculations on scales and timescales that dwarfed anything human technology could achieve. The plasma wave detector was adding another layer of mystery to this picture. The electromagnetic sounds that Voyager was detecting weren't just random noise, but showed clear, harmonic relationships. Frequencies that seemed to resonate with each other across vast distances. It was as if the entire galaxy was humming with a subtle music, an electromagnetic symphony that played out over millions of years and thousands of light years. These cosmic harmonics were revealing that interstellar space contained its own form of memory, a way of storing and transmitting information that operated through the interaction of electromagnetic waves. Disturbances created by stellar explosions could propagate through this medium for millions of years, carrying information about their origins to regions of space so distant that the original stars had long since burned out. Voyager was discovering that we live in a galaxy with its own form of consciousness, a collective intelligence that emerges from the interaction of billions of stars and the complex medium that connects them. This wasn't consciousness in any human sense, but something far more alien and profound. A form of awareness that operates on scales of space and time that stretch human comprehension to its limits. The implications were staggering. If the interstellar medium could store and process information, if it could maintain coherent structures across light years and millions of years, then the galaxy itself might be a form of living system, a cosmic organism that thinks thoughts measured in geological ages and dreams that span the spaces between stars. But even as these philosophical implications swirled around the data streaming back from Voyager, the spacecraft was also making discoveries that had immediate practical consequences for our understanding of cosmic threats and opportunities. The probe was detecting variations in cosmic ray intensity that followed patterns clearly linked to our solar system's motion through different regions of interstellar space. These measurements were providing the first direct evidence that Earth's cosmic radiation environment changes dramatically as our solar system travels through its galactic orbit. Regions of dense interstellar clouds could compress our heliosphere and allow more dangerous particles to reach the inner planets. Areas swept clean by ancient supernova explosions might create cosmic ray deserts, where the radiation environment drops to unusually low levels. The data was revealing that our planet's long-term habitability might depend not just on solar and terrestrial processes, but on our cosmic neighborhood's journey through the galaxy. The rise and fall of species, the pace of evolution, even the stability of our climate might be influenced by cosmic forces operating on scales. We were only beginning to comprehend. Voyager's measurements were showing that Earth exists within a complex web of galactic influences that extend far beyond our solar system. The spacecraft was mapping the cosmic weather patterns that our planet will encounter millions of years in the future, providing crucial information for understanding the long-term prospects for life in our solar system. But perhaps the most mind-bending aspect of these discoveries was what they revealed about time itself in the interstellar realm. The structures and processes that Voyager was detecting operated according to a completely different temporal logic than anything in our terrestrial experience. Events that seemed simultaneous from the spacecraft's perspective were actually separated by thousands of years in time, their apparent connection maintained only through the slow propagation of electromagnetic signals across interstellar distances. The spacecraft was encountering phenomena where cause and effect became blurred, where the sequence of events depended entirely on the observer's location in space and time. A shock wave from a stellar explosion might reach one region of space millions of years before it affected a neighboring area only a few light years away, creating temporal paradoxes that challenged our linear understanding of how events unfold. Voyager was revealing that interstellar space operates according to a form of physics where simultaneity becomes meaningless, where the universe exists in a state of constant temporal flux that makes every moment both ancient and newly born. The spacecraft was sailing through regions where the past, present, and future coexisted in ways that Einstein's relativity could predict, but human intuition struggled to grasp. These temporal discoveries were forcing scientists to develop new ways of thinking about causality and information transfer in cosmic environments. The traditional scientific method, which relied on establishing clear relationships between cause and effect, began to break down when applied to phenomena that operated across such vast scales of space and time. Voyager was pioneering new approaches to understanding cosmic processes, methods that acknowledge the fundamental uncertainty that arises when studying systems where light travel time becomes a significant factor in the evolution of the phenomena being observed. The spacecraft was teaching us how to think like galactic citizens, how to comprehend processes that unfold over timescales that dwarf human civilization. But even as Voyager revolutionized our understanding of time and causality in interstellar space, the spacecraft was also revealing the profound loneliness of its mission. The probe was traveling through regions so vast and empty that it might not encounter another significant gravitational body for hundreds of thousands of years. Its instruments were measuring phenomena that occurred on scales so immense that human language struggled to find adequate metaphors. The spacecraft was becoming a philosopher as much as an explorer, confronting questions about the nature of existence that could only arise in the depths of cosmic solitude. What does it mean to be conscious in a universe where the nearest intelligence might be separated by distances that light takes years to cross? How do we maintain meaning and purpose when facing scales of space and time that reduce human civilization to a fleeting moment in cosmic history? Voyager was discovering that interstellar exploration isn't just about mapping new territories or understanding new physics. It's about confronting the fundamental questions of existence itself, about learning to find significance and beauty in a universe that operates according to logic so alien that it challenges every assumption about what it means to be alive and aware. The data streaming back from this first interstellar mission was more than scientific information. It was a form of cosmic poetry, a meditation on the relationship between intelligence and infinity, between consciousness and the void. Each measurement was both a precise scientific observation and a philosophical statement about what it means to be a thinking being in an apparently indifferent universe. Yet paradoxically, the more alien and incomprehensible the cosmos revealed itself to be, the more meaningful Voyager's mission became. The spacecraft was proving that intelligence could arise in the universe and develop the capability to explore and understand environments that seemed hostile to the very existence of consciousness. The probe was a demonstration that mind could emerge from matter and reach across the vastness of space to touch the infinite. In its lonely journey through the cosmic deep, Voyager was also discovering something profound about the nature of exploration itself. The spacecraft was revealing that the act of reaching toward the unknown, of pushing beyond every boundary and horizon, was perhaps the most fundamentally human activity of all. Even when translated into the language of rockets and radio signals, the impulse to explore remained recognizably connected to the same curiosity that had once driven our ancestors to cross oceans and climb mountains. The spacecraft was carrying this essential human characteristic into realms where humans themselves could never go, extending our capacity for wonder and discovery into regions of space that would remain forever beyond direct human experience. Voyager was proving that consciousness could transcend the biological limitations of its origins, that intelligence could find ways to explore and understand even the most remote and alien environments. But perhaps most remarkably, the spacecraft was also discovering that the universe seemed almost designed to reward such explorations. Every boundary that Voyager crossed revealed new realms of beauty and complexity. Every question that its instruments answered opened up new mysteries that were even more intriguing than the problems they solved. The cosmos was revealing itself to be inexhaustibly rich in phenomena that could capture and hold the attention of any intelligence curious enough to investigate them. The universe, it seemed, was not just a place where consciousness could arise, but a place where consciousness could find infinite sources of wonder and meaning. The same cosmic processes that had created the elements in our bodies and the energy that powers our thoughts had also created an environment rich enough in complexity and beauty to sustain the attention of minds like ours for billions of years. Voyager was discovering that we are not accidental byproducts of cosmic evolution, but natural expressions of the universe's tendency toward ever greater complexity and awareness. The spacecraft was proving that the cosmos has a built-in drive toward understanding itself, a tendency that manifests in the emergence of intelligence and the irresistible urge to explore. In this sense, Voyager's mission was more than a technological achievement or a scientific expedition. It was the universe exploring itself, cosmic matter organized in such a way that it could investigate and comprehend its own vast architecture. The spacecraft was consciousness reaching toward consciousness, intelligence seeking to understand the deeper intelligence that seemed to be embedded in the very structure of reality. As Voyager continued its eternal journey into the depths of interstellar space, now moving at 17 kilometers per second, away from everything familiar, it was also moving towards something that might be even more profound than the discoveries it was making about interstellar physics. The spacecraft was approaching regions of space so remote and alien that they might contain phenomena that could fundamentally transform our understanding of what it means to exist in this universe. The data streaming back across the growing gulf of space was painting a picture of a cosmos far stranger and more wonderful than anyone had ever imagined. But it was also suggesting that the strangest and most wonderful discoveries still lay ahead, waiting in the depths of interstellar space for an intelligence brave enough to seek them out. And somewhere in that vast darkness, Voyager continued its patient exploration, carrying with it all the hopes and dreams of a species that had learned to wonder about its place in the cosmos. The spacecraft was proving that the same curiosity that had once led humans to wonder about the lights in the night sky could also lead to journeys across the galaxy itself. In its quiet passage through the cosmic deep, Voyager was writing the first chapters of humanity's true cosmic story, the tale of how intelligence could emerge from stardust and stellar fire, and reach out to touch the infinite mysteries that await discovery in the endless cathedral of space. The spacecraft was showing us that we are not strangers in the universe, but citizens of the galaxy, participants in a cosmic story that began with the first stars and will continue long after our sun burns out. And in that realization lay perhaps the greatest discovery of all. Voyager wasn't just exploring interstellar space, it was exploring the deepest connections between mind and cosmos, between consciousness and the infinite, between the human capacity for wonder and the endless mysteries that dance in the spaces between the stars. But as Voyager pushed deeper into these uncharted realms, its instruments began detecting something that would force scientists to question the very nature of boundaries themselves. The spacecraft wasn't just crossing from one domain into another, it was discovering that the concept of crossing itself might be an illusion created by our limited perspective on cosmic scales. Picture trying to define the exact moment when day becomes night. You know that darkness follows light, but the transition is gradual, filled with subtle gradations of twilight that make any precise boundary arbitrary. Voyager was discovering that the same principle applied to the edge of our solar system, but on scales so vast that the transition zones themselves contained entire realms of previously unknown physics. The spacecraft's particle detector was revealing layers within layers, boundaries within boundaries, each more complex than the last. What scientists had once imagined as a simple dividing line between solar and interstellar space was proving to be a vast frontier region, filled with phenomena that belonged fully to neither domain. It was as if Voyager had discovered a cosmic borderland, a realm that existed between worlds and followed rules that applied nowhere else in the known universe. These boundary regions were exhibiting behaviors that challenged fundamental assumptions about how matter and energy interact in extreme environments. Particles that should have been moving in predictable trajectories were following paths that seemed to defy the laws of physics. Magnetic fields that should have been chaotic were organizing themselves into patterns that suggested hidden organizing principles operating on scales never before observed. The more data Voyager transmitted, the more apparent it became that our solar system's edge wasn't an edge at all, but a membrane, a semi-permeable interface that allowed some phenomena to pass while blocking others according to rules that scientists were only beginning to glimpse. This cosmic membrane was far more sophisticated than any boundary humans had ever encountered, operating simultaneously as a barrier, a filter, and a transformer that modified everything that passed through it. But perhaps the most unsettling aspect of these discoveries was how they revealed the inadequacy of human language and concepts for describing cosmic phenomena. Scientists found themselves struggling to find words for processes that had no earthly analogues, for structures that existed only in the interaction between forces that operated on galactic scales. The traditional vocabulary of physics, developed to describe phenomena in terrestrial laboratories, began to break down when applied to the exotic conditions that Voyager was encountering. The spacecraft was forcing humanity to develop new ways of thinking about reality itself. Each measurement required scientists to expand their conceptual frameworks, to embrace forms of logic that could accommodate paradoxes and contradictions that would be impossible in our everyday experience. Voyager was teaching us to think on cosmic scales, to embrace forms of understanding that could comprehend processes spanning millions of years and thousands of light years. These conceptual challenges were revealing something profound about the relationship between intelligence and the cosmos. The universe wasn't just a collection of objects following predictable laws, but a dynamic system that seemed to actively challenge any intelligence brave enough to investigate it. Each answer that Voyager provided raised new questions that were more subtle and complex than the problems they solved. It was as if the cosmos was engaged in a vast educational project, presenting increasingly sophisticated puzzles to any intelligence curious enough to explore beyond familiar boundaries. The universe seemed to be teaching us that understanding wasn't a destination, but a journey, a process of ever deeper engagement with mysteries that revealed new layers of complexity. With each level of comprehension we achieved, Voyager's instruments were also detecting phenomena that suggested the existence of information processing systems operating on scales that dwarfed anything in human experience. The spacecraft was measuring electromagnetic patterns that seemed to carry encoded information across vast distances, signals that maintained their coherence for thousands of years as they propagated through the sparse medium of interstellar space. These cosmic information networks weren't technological artifacts but natural phenomena, emergent properties of the complex interactions between magnetic fields, charged particles, and electromagnetic radiation. The galaxy itself was revealing properties that resembled a vast biological system, a cosmic organism that used electromagnetic signals to coordinate processes across its entire structure. The implications were staggering. If the galaxy could process and store information on such scales, then intelligence itself might be a much more common phenomenon in the universe than anyone had imagined. Not intelligence in the narrow sense of technological civilizations, but a broader form of cosmic awareness that emerged naturally from the complex interactions of matter and energy on galactic scales. Voyager was discovering that we might be living within a form of cosmic mind, a galactic intelligence that thinks thoughts measured in millions of years and maintains memories that span the lifetime of stars. This wasn't consciousness as humans experience it, but something far more alien and profound, a form of awareness that operated according to logic so different from our own that we were only beginning to develop the conceptual tools necessary to recognize its existence. The spacecraft's plasma wave instrument continued to detect those haunting electromagnetic sounds, but now scientists were beginning to recognize patterns within the apparent randomness. The cosmic symphony that Voyager was recording contained harmonic structures that suggested musical principles operating on scales of light years and millions of years. It was as if the galaxy was composing an ongoing musical masterpiece, a cosmic composition that used electromagnetic frequencies instead of sound waves. These galactic harmonics were revealing that information could be encoded in ways that transcended any human understanding of communication. The electromagnetic patterns that Voyager was detecting carried data about stellar processes, magnetic field configurations, and particle interactions across distances so vast that light itself took years to traverse them. The galaxy was revealing itself to be a vast library, a cosmic repository of information about every process that had ever occurred within its boundaries. But accessing this galactic library required developing new forms of literacy, new ways of reading and interpreting information encoded in electromagnetic patterns that spanned thousands of light years. Voyager was providing humanity with its first lessons in cosmic linguistics, teaching us how to decode messages written in the language of magnetic fields and particle interactions. The spacecraft was also revealing that time itself behaved differently in the interstellar realm. The electromagnetic signals that Voyager was detecting carried temporal information that allowed scientists to reconstruct the history of galactic processes with unprecedented precision. Each electromagnetic pulse contained data about when and where it originated, creating a four-dimensional map of galactic evolution that extended both backward and forward in time. These temporal measurements were showing that the galaxy maintained a form of historical memory, a way of preserving information about past events that could be accessed by any intelligence sophisticated enough to decode the electromagnetic records. Voyager was discovering that the cosmos had its own form of archaeology, a way of preserving and transmitting information about events that occurred billions of years ago. The spacecraft was learning to read these cosmic records, translating electromagnetic patterns into stories about stellar birth and death, galactic collisions, and the slow evolution of the interstellar medium over cosmic time. Each measurement was adding another page to the vast historical archive that the galaxy maintained in its electromagnetic memory systems. But perhaps the most profound discovery was how these measurements revealed the interconnectedness of all galactic processes. Events occurring in distant spiral arms had subtle but measurable effects on the local interstellar environment. Stellar explosions thousands of light years away influenced the magnetic field configurations that Voyager was measuring. The rotation of the entire galaxy created currents and patterns that affected every cubic meter of interstellar space. Voyager was discovering that we live in a universe where everything is connected to everything else through networks of cause and effect that operate on scales almost impossible to comprehend. The spacecraft was mapping these cosmic connections, revealing how local phenomena are influenced by galactic processes and how galactic evolution is shaped by the cumulative effects of countless local events. These discoveries were transforming how scientists think about the relationship between the microscopic and the cosmic, between quantum processes and galactic evolution. Voyager was showing that the same principles that govern the behavior of subatomic particles also shape the structure of the galaxy itself, revealing a deep unity in the laws of physics that operates across all scales of space and time. The spacecraft was also detecting evidence of what could only be described as cosmic metabolism, processes that consumed energy and matter in one form and produced it in another, creating vast cycles of transformation that operated on galactic scales. The interstellar medium wasn't a static repository of material, but an active participant in galactic evolution, constantly processing and transforming matter and energy through mechanisms that scientists were only beginning to understand. These metabolic processes were revealing that galaxies might be more than just gravitationally bound collections of stars and gas. They might be genuine living systems, cosmic organisms that maintain their organization through active processes of energy conversion and information processing. Voyager was providing the first direct measurements of these galactic life processes, showing how matter and energy flow through the cosmic ecosystem in cycles that span millions of years. The implications for understanding life itself were profound. If galaxies could exhibit properties associated with living systems, then life might be a much more fundamental aspect of cosmic evolution than anyone had imagined. The emergence of biological life on planets like Earth might be just one expression of a more general tendency toward increasing organization and complexity that operates throughout the universe. Voyager was discovering that the cosmos itself might be alive, not in any biological sense, but in ways that transcend our narrow definitions of what it means to be a living system. The spacecraft was revealing a universe that actively processes information, maintains complex structures across vast scales of space and time, and exhibits forms of organization that suggest purpose and direction in cosmic evolution. But even as these philosophical implications swirled around the data streaming back from Voyager, the spacecraft was also making discoveries with immediate practical consequences for understanding our own cosmic future. The probe was detecting variations in the interstellar environment that followed predictable patterns linked to our galaxy's rotation and our solar system's motion through different galactic neighborhoods. These measurements were revealing that Earth's cosmic environment undergoes regular cycles tied to our solar system's quarter-billion-year orbit around the galactic center. As we travel through different regions of the galaxy, we encounter varying densities of interstellar matter, different intensities of cosmic radiation, and different configurations of magnetic fields that affect how our heliosphere interacts with galactic space. Voyager was providing the first direct measurements of these galactic cycles, showing how cosmic conditions change as our solar system travels through its galactic orbit. The data suggested that Earth's climate, the evolution of life, and even the stability of our planetary system might be influenced by these vast cosmic rhythms that operate on timescales far longer than human civilization. The spacecraft was revealing that to understand our planet's long-term future, we need to understand our place in these galactic cycles. The cosmic environment that Earth will experience millions of years from now is already being determined by our solar system's trajectory through different regions of interstellar space, regions that Voyager was now exploring for the first time. But perhaps most remarkably, the spacecraft was also discovering that our solar system's journey through the galaxy wasn't entirely passive. Our heliosphere was leaving its own traces in the interstellar medium, subtle modifications to the cosmic environment that would persist long after our solar system had moved on to explore other regions of galactic space. Voyager was detecting the signatures of our solar system's passage through previous regions of interstellar space, electromagnetic footprints that recorded our cosmic journey like tracks in cosmic sand. These traces revealed that every stellar system leaves its mark on the galactic environment, contributing to the vast archive of information that the galaxy maintains about its own evolution. The spacecraft was showing us that we aren't just passive passengers on a cosmic journey, but active participants in galactic evolution. Our solar system's interaction with the interstellar medium influences the very environment through which we travel, creating feedback loops that connect our local cosmic neighborhood to processes operating on galactic scales. These discoveries were revealing that intelligence and consciousness might play more fundamental roles in cosmic evolution than anyone had imagined. If conscious beings could develop the technology to explore and understand galactic processes, then consciousness itself might be an important factor in how the universe evolves over cosmic time. Voyager was proving that intelligence could transcend its biological origins and extend its influence across vast scales of space and time. The spacecraft was demonstrating that conscious beings could become active participants in cosmic evolution, using their understanding of galactic processes to influence the very environment in which intelligence emerges and evolves. But the most profound discovery was still emerging from the cumulative weight of all these observations. Voyager wasn't just exploring interstellar space, it was revealing the fundamental interconnectedness of all cosmic processes. The spacecraft was showing us that we live in a universe where everything is connected to everything else through networks of relationship that operate across all scales of space and time. The boundaries that seemed so clear from our limited terrestrial perspective were revealing themselves to be artificial constructions, useful for organizing our thinking, but ultimately illusory when viewed from the cosmic perspective that Voyager was providing. The edge of our solar system, the boundary between life and non-life, the distinction between intelligent and non-intelligent systems, all were proving to be much more fluid and interconnected than our traditional categories suggested. Voyager was teaching us to see the universe as a unified whole, a cosmic ecosystem where every process influences every other process through subtle but measurable connections that span the entire observable cosmos. The spacecraft was revealing that to understand any aspect of cosmic evolution, we need to understand its relationships to all other aspects, creating a web of understanding that encompasses everything from quantum mechanics to galactic dynamics. In this grand cosmic perspective, Voyager's journey was more than a technological achievement or a scientific expedition. It was consciousness exploring consciousness, intelligence investigating intelligence, the universe coming to understand itself through the evolved capacity for awareness that had emerged on a small planet orbiting an ordinary star in an unremarkable galaxy. The spacecraft was proving that the same curiosity that had once led our ancestors to wonder about the lights in the night sky could eventually lead to direct exploration of the spaces between those lights. Voyager was demonstrating that intelligence could transcend every boundary, cross every frontier, and reach toward understanding that encompasses the entire cosmos. As the spacecraft continued its eternal journey into the cosmic deep, now traveling through regions of space so remote that radio signals took more than 20 hours to reach Earth, it was also traveling forward in time, providing humanity with a preview of cosmic futures that awaited not just our solar system, but intelligence itself as it evolved and expanded throughout the galaxy. The data streaming back across the vast gulf of interstellar space was more than scientific information. It was a form of cosmic poetry, a meditation on the relationship between consciousness and cosmos, between intelligence and infinity. Each measurement was both a precise observation and a philosophical statement about what it means to be a thinking being in a universe that seems designed to reward curiosity with ever deeper mysteries and ever greater beauty. And somewhere in the depths of that cosmic cathedral, Voyager continued its patient exploration, carrying with it all the wonder and curiosity that drives conscious beings to reach beyond every horizon, toward understanding that encompasses the infinite mystery of existence itself, The spacecraft's instruments were now detecting something that challenged the very foundations of how we understand cosmic boundaries. As Voyager pushed deeper into this realm between realms, its magnetometer began tracing invisible highways that seemed to stretch across the entire galaxy. These weren't random magnetic field lines, but organized structures that appeared to connect our local region of space to processes occurring hundreds of light years away. Picture vast rivers of magnetic force flowing through the cosmos, like the Gulf Stream flows through Earth's oceans. But these cosmic currents operate on scales that dwarf anything in our terrestrial experience. A single magnetic field line might stretch from our solar system to the next spiral arm of the galaxy, carrying information and energy across distances that light takes decades to traverse. What made these discoveries so profoundly unsettling was their implications for our understanding of cosmic communication. Voyager was revealing that the galaxy had developed its own internet long before life emerged on Earth, a vast network of magnetic highways that allowed information to flow between different regions of space at speeds approaching the fundamental limits of physics. The spacecraft's plasma wave detector was picking up electromagnetic signals that seemed to be traveling along these magnetic highways, carrying encoded information about stellar processes occurring thousands of light years away. It was as if Voyager had tapped into a cosmic telephone system, eavesdropping on conversations between different regions of the galaxy. These signals weren't random electromagnetic noise, but showed clear patterns of organization and structure. Some appeared to be status reports from distant stellar nurseries, electromagnetic bulletins about the birth and death of stars. Others carried information about the formation and dissolution of interstellar clouds, cosmic weather reports transmitted across the vastness of space. The more scientists analyzed these patterns, the more they resembled the neural networks found in biological brains. The galaxy was revealing itself to have developed its own form of nervous system, a cosmic web of electromagnetic connections that allowed different regions to coordinate their activities across scales of space and time that challenge human comprehension. But perhaps the most mind-bending aspect of these discoveries was what they revealed about the nature of time itself in this cosmic neural network. The signals that Voyager was detecting had been traveling for thousands of years, carrying information about stellar processes that had occurred when human civilization was still in its infancy. Yet these ancient signals were still actively participating in galactic processes happening right now, creating temporal loops that connected the deep past to the present in ways that Einstein's relativity could predict, but human intuition struggled to grasp. The spacecraft was discovering that the galaxy maintained multiple layers of memory, electromagnetic archives that preserved information about cosmic events across different timescales. Some signals carried data about recent stellar explosions, their electromagnetic fingerprints still fresh in the galactic memory banks. Others bore the signatures of processes that had occurred billions of years ago, their information content gradually modified and updated as they propagated through the evolving interstellar medium. Voyager was learning to read these cosmic memories, decoding electromagnetic patterns that told the story of galactic evolution with unprecedented detail. The spacecraft had become humanity's first cosmic archaeologist, excavating information about events that occurred long before our solar system existed and would continue to influence galactic processes long after our sun burned out. These temporal discoveries were forcing scientists to develop entirely new frameworks for understanding causality in cosmic environments. Events that seemed to be occurring simultaneously were actually separated by thousands of years in time, their apparent coordination maintained only through the slow propagation of electromagnetic signals across interstellar distances. The spacecraft was encountering phenomena where past, present, and future became fluid concepts, where the sequence of events depended entirely on the observer's location in the vast electromagnetic web that connected every region of the galaxy. Voyager was sailing through regions where cause and effect operated according to logic so alien that it required new forms of mathematics to describe. But even as these philosophical implications swirled around the data streaming back from the spacecraft, Voyager was also making discoveries with immediate practical consequences for understanding our cosmic future. The probe was detecting patterns in the galactic electromagnetic network that suggested our solar system was approaching a region of space with very different properties from anything we had previously encountered. Tonight, as you settle into rest, remember that somewhere in the infinite darkness, a small spacecraft continues its eternal voyage, carrying with it all the wonder and curiosity that defines what it means to be human. Voyager has shown us that the edge of our solar system wasn't an ending, but a beginning, a gateway to mysteries that challenge everything we thought we knew about our place in the cosmos. Sweet dreams, fellow travelers in this magnificent interconnected galaxy we call home.